So in the first problem, we are given straight away that VDS is equal to 0, and you know that the current equation, the drain current equation, if you have an NMOS transistor and current is flowing like that, this must be the drain and the source, and that current equation, the equation ID is Kn prime W by L times Vmin, sorry, not Vmin, VGS minus VT, VGS minus VTN minus Vmin by 2 times Vmin, right? Now since VGS is equal to 0 and Vmin is equal to min of VDS, VDSAT and VDSAT n and VGS minus VTN, since these other two quantities are greater than 0, right? Because VGS is VDD, VDD minus VTN is VDD is clearly greater than VTN, so that's greater than 0. This is equal to 0. Vmin comes out to be 0, which means this is now 0 into something, so ID is equal to 0 is what we get. So that's the first answer. So in the second question, we are given a length of 2 lambda, which means that it's a short channel transistor, which means lambda n is 0.07, or since I've already said it's an NMOS transistor, lambda is 0.07 and VD sat n is 0.4. So short channel effects do apply. VGS minus VTN is, since VSB is 0, we have VTN is equal to 0.4 and VGS minus VTN is therefore 0.7 and VDS is 0.2, which means Vmin, which is the minimum of VGS minus VTN, VDS and VD sat n will come out to be 0.2, giving us that VDS is the minimum, therefore we are in the linear region. So now that we know what Vmin is and what VGS minus VT is and what VDS is, we can go ahead with calculating what the drain current will be. So the drain current is Kn prime W by L into VGS minus VT times Vmin by 2 times Vmin into 1 plus lambda VDS. Because it's a short channel transistor, I've had to include the lambda VDS component as well. So this works out to 48.6 microamps. So now let's look at question 3. So same, it's a short channel transistor, L is 2 lambda and VGS equal to 0.3, VDS volts, VDS is equal to 1 volt. Now you've increased VDS and reduced VGS, so you expect that it goes into the saturation region, but with the slight caveat that now VGS is less than VT. VTN is 0.4 volts, right? So therefore you're in the cutoff region and we've not assumed any subthreshold current. So therefore this is in the cutoff region with current of 0. So let's look at the fourth question. In it, we have that the W by L is 4 lambda by 2 lambda, which is equal to 2. So therefore, the channel length L of 2 lambda means it's a short channel device, which means that lambda equal to 0.07 and VD sat n is equal to 0.4. Now if VGS is, since VSB is 0, VTN is equal to 0.4, which means VGS minus VTN, which is 2 minus 0.4, is equal to 1.6 and VDS is 2 volt. So that means the minimum of VD sat n, VGS minus VT and Vmin is going to be 0.4 and thus we are in the velocity saturation region. Now substituting this in our equation for the drain current, we get that the drain current expression comes out like this. Kn prime W by L Vgs minus Vt into Vmin by 2 times Vmin into 1 plus lambda Vds, right? And so the drain current comes out as 255.36 microns. Yeah, so in the fifth question, it's fairly straightforward. We've been given that Vgs is 0, and since now this is less than Vtn of 0.4 volt, and since VSB is 0 volt, Vtn will be 0.4 volt, we assume the cutoff condition for which the level 1 SPICE model says the current is 0, and so therefore we have 0 as the current. So in the sixth question, we have VGS is equal to VDD of 2 volt and VDS is 0.5 volt, which means of course that VGS minus VT, because VSB is 0 volt, this is equal to the VTN is equal to 0.4 volt and VGS minus VTN is 1.6. So, and also now that it's a long channel transistor, we can assume that VD sat n is greater than VDD itself, and this means that it's never going to be possible for VGS minus VT to be because we assume that VDD is the maximum voltage that we can apply. We have VGS minus VT comma VDS are both less than VD sat n, and so we won't even include VD sat n in the Vmin expression. So this is VDS is 0.5. That means Vmin, which is the min of these two, is equal to 0.5. And yeah, since VDS has come out as the minimum, this is in the linear region, right? So now that we're in the linear region, let's find out what the value of the current is. Vmin has come out to be 0.5. That means ID, the current into the drain, ID is equal to Kn prime, which is 200 micro, times W by L, which is 40 by 20, which is 2, times Vgs minus Vt, which is 1.6, minus Vmin by 2, which is 0.5 by 2, times 0.5 into 1 plus lambda n, which is 0 because it's a long channel transistor. So lambda n is 0 times VDS of 0.5. Right? So this works out to be 400 micro times 2 into 0.5 is 1. So 1.6 minus 0.25 times 1 because that's 0. And if I were to plug this into a calculator, so sorry, this is not 400 micro, this is 200 micro. Plugging this into the calculator, we get 200 into 1.6 minus 0.25, which is 270 microamps. So in question number 7, we are asked to find what the maximum current deliverable by the NMOS transistor of size W by L 4 lambda by 2 lambda and VSB is equal to 0 volt is. So we know that for a short channel transistor, the ID VDS curve looks like this. It's a monotone increasing function. So that means that the maximum value of the y-axis will be obtained at the furthermost point to the right on the x-axis, right? Monotone increasing, that's why. So it's only going to be at VDS is equal to VDD, where you get the maximum value of ID. We also know that there are various curves for VGS of various values. So we'll have to take the highest possible VGS value, that is also the curve corresponding to VGS is equal to VDD, to get the peak current value drain current value for this NMOS, right? So yeah, we'll have to solve this question for VGS and VDS equal to VDD, and it just so happens that it's exactly the same as the wording of question 4, right? Where you got the answer to be this. And thus, this is the answer of question 7. In question 8, we are asked what the maximum current is again, except the length is now 20 lambda. W by L is still the same, but since it is now a long channel transistor, we'll have VT, we'll have no channel length modulation, and also we'll have that VD sat n is greater than any possible VGS minus VTN and VDS, right? So it's not going to be included in that Vmin expression. Now let's find the maximum current. So this is going to be at VGS is equal to VDD and VDS is equal to VDD. Since VSB is 0, we know our VTN is 0.4 volt. So this means ID, which is mu and Cox W by L times VGS minus VT, which is 2 minus 0.4 minus Vmin, which given that VGS is equal to VDD, that means VGS minus VT will be less than VDD, less than VDS. So that is going to be VGS minus VT is the Vmin, which is of course that this is in the saturation region. So that's now 1.6 is Vmin divided by 2 times 1.6. So of course now the inside will simplify to 1.6 minus 1.6 by 2, which is 1.6 by 2, which is 0.8. Plugging this into the calculator, and of course we have not taken the channel length modulation because lambda is equal to 0. Now plugging this into the calculator, we've got 200 micro into 2 into 0.8 into 1.6, which is 512 micro. Now in question 9, we have been given a body bias for the NMOS transistor. So, and we've also been given a gamma and psi as parameter. So let's find the threshold voltage of this transistor. VTHN is equal to VTH0 plus gamma times square root of mod VSB plus psi s minus square root of mod psi s, right? So for us this evaluates to 0.4 plus gamma is 0.4 times square root of VSB is 0.12. So VSB plus psi s both are positive, so I'm not going to take the mod. So it's 0.12 plus 0.3, which is psi s, minus square root of 0.3, right? This is equal to 0.4 plus 0.4 times square root of 0.42 minus square root of 0.3. Evaluating this, we get square root of 0.42 minus square root of 0.3 is equal to 0.1 almost. So this is equal to 0.4 plus 0.04, which is 0.44. Or, so let's proceed to calculate the drain current. For VGS is equal to VDD, so VGS minus VT is VDD. VGS minus VTN is VDD minus 0.44, which is VT, which we've calculated here, which is equal to 1.56. And since this is less than the drain voltage of 2 volt, VDS of 2 volt, this is going to be equal to Vmin, and we've not taken VDSAT because it's a long channel transistor. So ID is equal to mu n Cox W by L into Vgs minus Vt minus Vmin by 2 times Vmin, and we've not taken the 1 plus lambda VDS because it's a long channel transistor, so lambda is equal to 0. So this is equal to 400 micro into 1.56 by 2 times 1.56. Plugging this, we get 400 into 1.56 squared divided by 2, which is 486.7. And the region is saturation because VDS is greater than VGS minus. So for the final question, we are given a VBS of 0.05 with the same gamma and psi s and asked to find the threshold voltage of the transistor in millivolts. So again, VTHN is equal to VTH0 plus gamma times square root of mod of psi s plus VSB minus square root of mod psi. So this is equal to 0.4 plus 0.4 times square root of 0.3 minus 0.05 minus with psi s of 0.3, right? So this is equal to 0.4 plus 0.4 plus square root of 0.25 minus square root of 0.3, and plugging this into the calculator gives us square root of 0.25 minus square root of 0.3 is equal to minus 0.047, and this into 0.4 plus 0.4 gives us 0.3809, which is 381 millivolt approximately, right? And notice that L is 2 lambda, so it's a short channel, which means lambda n is 0.07 and VD sat n is 0.4, right? So now we have to calculate for VGS equal to VDD, and VDS is 1 volt. So this means that VGS minus VTN is 2 minus 0.381, which is 1.619, which is approximately 1.62 volt. And VDS is equal to 1 volt. Of course, VD sat n is 0.4, so Vmin equal to min of VGS minus VT, comma VDS, comma VD sat n. This will come out to be 0.4, giving us the region as velocity saturation. And finally, the drain current is equal to 200 micro times W by L, which is 2, times Vgs minus Vt, which is 1.62, minus Vmin by 2, times Vmin times 1 plus lambda VDS, right? Solving for this, we get 400 micro into 1.62 minus 0.2, which is 1.42, times 0.4 times 1.07, which if I plug into the calculator is 400 micro into 1.42 into 0.4 into 1.07, 243.1 microamps.